Hello everyone. Please let me know if I am completely audible and my screen is visible to you. Anyone? Please just drop a comment so that we can start. Anyone? Okay, someone is writing hello. Okay, so Ayush, am I audible? Just drop a comment if I am audible or not. Just a yes or no. Okay. Otherwise, I am starting. Okay. So let me take you to a recap of what we have done. Okay. Thank you, Ayush. So precap was like we have covered all our range query data structure. We have like this is the 11th lecture in this series and we have covered all the range query data structures. Okay. So what do we mean by range query data structures? That we have already seen. So we have covered prefix structure, both 1D and 2D. Then we have covered Fenwick square root decomposition. And using the square root decomposition technique, we have also implemented Mohs algorithm. Okay. And then along with this, after that we have discussed the Fenwick tree, or you can say it as binary index tree, and then segment trees. We have solved some problem on segment trees, and then we have implemented merge sort tree. Okay. And along with this, we have also talked about the lazy propagation for lazy propagation. We have also talked about the lazy propagation on segment trees for the range updates. So this is what we have seen till now, and in the Fenwick tree we have also seen the order statistic tree. Okay. So like this is the complete summary of the thing which we have discussed in the last 10 lectures, and we have completed with our range query data structure. If you are like, if you know all of these things, and like this is just sufficient to solve most of the range query problems. Okay, this is just data structure and you need to just practice some more problems and you will be getting a good hold on the range query problems. Okay, so this is what we have done till now. Okay. And then for today's lecture, what we are going to do today is, our plan is, we are going to start with the disjoint set union. Okay, disjoint set union, it is also one of the data structure, but it is not a range query data structure. Basically its application is mostly in the graph algorithms. Okay, so they are mostly used in the graph algorithms. Now what is actually a disjoint set, and how it is how we are going to use it, that we have to discuss in today's lecture. But before that, to understand this particular thing, uh, we are taking a problem statement, and we'll try to solve that problem statement, and in that by using that problem statement we will be deriving our data structure. Okay, so this is what our plan is. So like, let me tell you the problem statement. What is the problem statement? So the problem statement says that, like, suppose we are having n people. Okay, say number are from 1 2 3 to n, and we are, after that we are given m queries. Okay, in m queries we can make we will be given x and y values, and it means that x and y are friends. Okay, so we have to make them friends. Now what is happening here, now suppose if one is a friend of two, like in one query you are getting 1 and 2, so that means 1 and 2 is now a friend, so you can represent it as a set. Now if any one of them is a friend of any other third person, then both of this group is going to be the friend of that particular person. Okay, so suppose if you are having a group of friends, okay, suppose we are having n number of friends here, and if any one of them becomes friend with the third person, then the complete group is going to be the friend with that particular person. Okay, so suppose if I am writing like 1 is a friend of 2, and suppose if 3 is a friend of 4, then it is obvious that 2 is also a friend of 4. Okay, sorry, because suppose if 1 is a friend of 2 and 3 is a friend of 4, and if 1 is also a friend of 4, in that case the 2 is also a friend of 4, because originally we are having 1, 2, 3, 4 as a separate identity. Now 1 is a friend of 2. Now in our set we are having 1 comma 2 as a group of friends. Okay, now again we are getting a query of 3 comma 3 to 4. Now 3 or 4 are each other's friend. Okay, so this is, we can make a set of these two friends. Then we are getting a query of 1 and 4, so 1 is in this group and 4 is in this group, and as these people are each other friends, then both of this set is going to combine, like all of them 1 2 3 4 would be friends of each other. Okay, so now I think it is clear to you like what I am going to give you as a query. So we are getting m queries, and in not queries but we are getting m inputs, and in the inputs we are getting two integers in which we are like telling that is this x and y person are going to be friend of each other. Okay, now after that we will be getting q queries. In q queries we will be getting some integers, like two integers, and we have to tell like whether these two are friends or not. Okay, so this is the problem statement. So yes, Ayush Sharma is saying that a problem statement is understood. Okay, so I think the problem statement is clear to everyone. um, Please like drop a comment if you are finding it difficult to understand the problem statement. Okay, otherwise we'll try to get to the solution of this one. Okay, now solution. What is the solution? So what very basic thing we can do here is, like suppose if 1 is a friend of 2, now we know that 1 and 2 are each other friends, and then 3 and 4 becomes each other friend. Now if 1 becomes the friend of 4, then what we can do is we can check all the values which are friend of 1. Okay, which is directly connected to this, and we can make all of them as a friend of this particular 4 value. And similarly we can do this, like all the values that is present in this set, we can make this particular all the values of this particular set as friend of all the values of this particular set. So in the worst case what could happen is, like this particular set is containing n elements and this particular set would be containing n elements. So if you make every person every other like every person a friend of every other person, so that would cost you n into n as a time complexity, and this is the worst solution. You cannot, like, if a single query is taking this much time, how you are going to solve q number of queries? Okay, so this is very inefficient solution. This is very inefficient solution, and we are not going to solve it by that way. Okay, so I think now you understood why this solution is inefficient. Okay, so what could be the better solution? What could be the better solution? So for the better solution, what we can do is we can like analyze this problem in terms of graph. Okay, so now suppose if we are analyzing this particular problem in terms of graph, then what is happening here? So suppose if like I am having these four values 1 2 3 and 4, and initially I am considering all of them as a node. Okay, now as 1 and 2 became friends of each other, what I am going to do is I am going to choose one of them as a root element, like say this is 1, and I am going to connect these two values, okay, in this manner. Okay, now as 3 and 4 become friends of each other, what I am going to do is I am going to connect this 3 with this 4. Okay, so this is something like a tree and we are just connecting some edges in this. Now the third query was 1 and 4 is going to be the friend. So what I am going to do is I am going to connect this 1 and 4, and now you can check here, like all of them are connected. Okay, so yes, this is what we are going to do. Whenever we are going to get a query, what we are going to do is we are going to connect both of them with a edge. Okay, but now suppose if x and y are first connected, then we know that these two belongs to some group. Okay, now if x and y gets connected, and say after some time like y's get connected to z, now if this thing happens, then this would be a group, this would be some another group. So like how I'm going to identify a particular group? So we have to have some, say, name for that particular group, or say some representation, or say some representative. Okay, or say some ancestor or parent. So there should be some parent of each group. Okay, so that like if this was one group, and suppose if w and x was in some other group, then we can check here like this x is belonging to this group and say z is belonging to this group, and as these two groups are different, that means no one of this no one no element from this group is a friend of this group. Okay, so then only we can identify this if we have some representations for this group. So we need some representative. So while we are connecting them, okay, so while we are connecting them, we need to provide some representative. Like if one is getting connected to two, then either one or two should like either one of them should be representative. So suppose we are making one as a representative, so we can say that yes, one is the parent of 2. Now suppose if one is getting connected to 3, then what we are going to do is we are making this one as a parent of 3 also. Okay, now suppose if 4 is getting connected to 5 in some query, now we know that like say we are making 5 as our parent, and this is 4, we are going to connect this 4 here. Okay, now we know that the parent of 2 is 1 and the parent of 3 is 1, and the parent of 1 is again 1, and the parent of 5 is 5, and the parent of 4 is 5. Now suppose if we want to check if 2 and 4 are friends of each other or not, then what we are going to do is yeah, can we directly use one person as a representative in one group? Yes, definitely, this is what we are doing here. Okay, so now yes, so we if we want to check if 2 is a friend of 4, okay, so you can check what is the parent of 2. So the parent of 2 is 1, and what is the parent of 4? So the parent of 4 is 5. So as these two parents are not matching with each other, that means they belongs to the different groups, hence they are not friends. Now suppose if we are checking for 2 and 3, so if we are checking for 2 and 3, the parent of 2 is 1 and the parent of 3 is also 1. So as both of them belongs to same parents, that means they falls in the same group, hence they both are friends. So yes, these two are friends. Now suppose if we are checking for 4 and 5, the parent of 4 is again 5 and the parent of 5 is 5. So as they both belongs to the same parent, we can say that yes, these two are friends. So I think you got the idea how we are going to do this. Now, so I think the idea for the solution is clear to everyone. Okay, so this is, and this idea is nothing but, in technical terms, this is called as disjoint sets. Why it is called as disjoint sets? We are having some, like we are having two sets. we are having some number of elements in this set and we are having some number of elements in the other set, and these two sets are disjoint. Okay, and then we are getting some query in which one element is say interacting with the another element, and then this two becomes another set. Okay, these two sets merges and becomes as a single set. Okay, so that's why this is called as disjoint. Initially they were disjoint and then some query came and then there were union of these two sets. Okay, this is why this is called as disjoint set union. Okay, okay, so I think this is clear to you. Now how we are going to implement this data structure? Now let us look at the implementation details. Okay, implementation details, how we are going to implement it. So the first thing is we need an array in which we will be representing the parent of each node. Okay, now suppose if we are having certain number of nodes like 1 2 3 4 5 6 7 8 9, suppose we are having 9 pupils. So initially all of them is going to be their own parent, because initially they were independent and like single entity, they are single entity. So initially all of them are their own parent. Okay, now what we are going to do is, now suppose if one is getting connected to 2, so the parent of 2 is going to get, the parent of 2 is changed to 1. So like we are going to have a parent array and that we are going to reflect in our parent array. So if like the parent of 2 is getting changed to 1, here instead of 2 we will be having 1. Okay, now suppose if again 3 and 2 gets connected, then what we are going to do, we are going to make the parent of 3 as 2. Okay, so the parent of 3 here would be 2, but you know the parent of 2 is already 1, so ultimately the parent of 3 is going to be 1 and the parent of 2 is also going to be 1. Okay, and similarly if 4 becomes parent of, like if 4 and 3 gets connected, then what you are going to do, you are going to make the parent of 4 as 3 and you are going to connect it in this way. Okay, and 4 is going to get connected here. So the parent of 4 is 3 but the parent of 3 is 2 and the parent of 2 is 1. So ultimately for all of these values the parent is going to be 1 only. Okay, so by this method, like you can connect directly. If you are getting like some queries 2 to 3, you can just connect that the parent, you can just make the parent of 2 as the parent as equals to 3. Okay, you don't need to care of anything else. So when you are finding the ultimate parent, then what you have to do, you have to just do the recursive calls to this. Like if you want to find the original parent of 4, what you will be doing is you will be finding the parent of 4 and you will be checking what is the parent of 4. So you know that the parent of 4 is 3, and if the parent of, then you will be checking what is the parent of 3. So the parent of 3 is 2, then you will be checking what is the parent of 2. The parent of 2 is 1. Okay, and what, then you will be checking what is the parent of 1. So the parent of 1 would be again 1. So as the parent of 1 is 1, so this is the complete representative, or say the ultimate representative of the group. Okay, so this is how you are going to get the parent of anyone. Okay, so this is one function we are going to implement, find parent. Okay, so in the find, like you can have a function implementation in find and you will be giving a value in this particular function, and that particular function will be returning you the parent of say x value. How we are going to do this, that we will discuss when we are going to code it. Okay, but I think the idea is clear, you have to do it recursively. Okay, so this is what we were doing, and what we have to do in union. So in the union we can just, like we can find the parent of anyone. Like if you have to connect x and y, you can just find the parent of x, say it px, you can find the parent of y py, and you can like make any one as the parent of other. Like you can make the y as the parent of x, or say px as a parent of py. You can do anything. Like suppose if you are having two sets, something like this, and if you want to connect these two sets, what you can do is you can call this thing as a parent, and you can just do this. and you can just connect this particular thing here. Okay, just like this. Or what you can do is you can make this thing as parent and you can connect it like this. Okay, so these are the two ways how you are going to connect, but they both will result in the same thing. That means ultimately these two groups are going to get connected. Okay, so this is what we are going to do. So I think the idea is clear to everyone, and at last will be like when we are getting the queries for x to y, like we have to check if x is a friend of y, then what we'll be going to do is we are going to find the parent of x, say px, and then we are going to find the parent of y, py, and if this px and py are equal, and this is not the immediate parent, this is the ultimate parent, like you can have a longer chains like 2 to 3, and if we are finding the parent of 3, it doesn't mean the parent of 3 is 2. The parent of 3 is, we are finding the ultimate ancestor or say ultimate parent, and that would be 1. Okay, so in that case this px represents the ultimate parent and the py represents the ultimate parent of y, and if both of them are equal, we are going to say that these are the friends, and if they both of them are not equal, we are going to say that these are, say, enemies or not friends. Okay, so this is the idea. So now we can like quickly code it out, but if you have any doubt, please ask, drop a comment in the chat box if you are having any doubts, okay, in the idea part, like whatever we have discussed till now. Otherwise we will be moving to codes. We are going to code it quickly. Any doubt? Okay, as we are not getting any doubts, uh, we are moving further to the coding part. Okay, so how we are going to code it? So let me first include the header files. Okay, I'll be including that later, but before, let me just implement the function part. Okay, so the function is vector int, and I need a parent. Okay, so and I'll initialize the value of the parent in the main function, in the driver function itself, and with this I have to implement two functions. One is say int find. Okay, so this would be one function, and the other function would be, say, uni, union. That is a, say, shorthand for union, and that would be connecting these two values with each other. Okay, so these are the two functions we are going to implement. We'll be implementing the driver function also, but that we'll do later on, but here we are just implementing these two functions. Okay, now what we have to do, like in the arguments we'll be getting int x, say we have to find the parent of x. Then if, like, what we have to do, we have to do it recursively. Like what would be the parent of x? So the parent of x would be, finding the parent of x. Okay, so we have to do it recursively. Okay, first we will be finding the parent of x, and then we will be finding the parent of that particular parent. So we have to go it recursively to find the ultimate parent, and when we have to stop, so in the recursion we should have some base case. So in the base case would be like, if parent of x, like at some point, if that particular node is only the parent of itself, then we are going to return that thing. Okay, so this would be our base case. So yes, just simple as this. This would give me the parent of x. Okay, and then we have to like implement the union function. So in the union function we have already discussed, first we have to find the parent of x. So in that case, say px is denoting the parent of x, we'll be finding the parent of x. So this is the function which is giving me the parent of x. So we'll be finding the parent of x, then we'll find the parent of y. So in that case, this would be parent of y. Okay. Now, if px is not equals to py, why we are writing this px is not equals to py? Because if px is already equal to py, that means already they belongs to the same group. So then at the time we don't have to connect this, okay, because they are already connected. And if it is not the case, then we'll be doing something. And what we'll be doing, we'll be making the parent of px equals to py. And yes, done. So yes, this is done. We have to just do this thing. So these two are the operations in this disjoint set union. Okay, so that's why sometimes this disjoint set union is also called as the union find structure. Okay, so sometimes this disjoint sets is also called as union find structure. Okay, union find structure. Why? Because in this we are implementing two functions, one is the union and another one is the find. So that's why this is can you explain the find function again? Okay, so like find is finding the parent of x. Okay, so how we are finding the parent of x? Like if you look this structure, so here what we are connecting, like suppose if we are getting some queries like this 1 to 2, 2 to 3, 3 to 4, and like this. So what you are doing, you are making 2 1 as a parent of 2. So here this edge you have connected. Then as you are getting another query of 2 to 3, like 2 and 3 are friends, then what you are doing, you are making 3 as a parent of 2, like 2 as a parent of 3. So this edge you are connecting. Now you are connecting 3 to 4. Now what you are doing, you are making 3 as a parent of 4. Okay, so this edge you have connected. Now if you want to find the parent of 4, so the parent of 4 here, if you look this at this array, the parent of 4 would be 3. Okay, that's how we have connected it. But is the parent of 4 is 3? No, the parent of 4 is not 3. We are not talking about the immediate parent, we are talking about the ultimate parent. So the ultimate parent of 4 is 1, because this group is only represented by a single element, that is the root element, and this would be the parent of all of the elements. Okay, so what we have to check, if we want to find the parent of 4, first we will be finding the parent of 4. So the parent of 4 here is 3. Then we'll be taking this 3 and we'll be finding the parent of 3, and that is 2. Then we'll be taking this 2 and we'll be finding the parent of 2, that is 1. And then we'll be checking parent of 1, and you will see that the parent of 1 is 1 itself. So at this point you have to stop and you have to return 1 as your result. Okay, so this you have to do recursively. So this is what we are doing here. First we are starting with the x, and we'll be finding the parent of x would be storing the immediate parent of x. Then you will be finding the parent to that parent, and you have to go till the parent of x becomes equals to x. And if the parent of x becomes equals to x, then in that case you have to return the x. So this is a recursive function and this is our base case. So I think now it is clear to you. If you, yes or no, you can just drop a comment. Okay, so yes, we have implemented these two functions, and now we are going to analyze the time complexity. Okay, time complexity. Okay, now time complexity, we are going to analyze the time complexity. So what we are doing here is we are finding parent, and suppose if we are having a structure like this, if we are having a structure like this, 1 is connected with 2, and then this is further connected with 3, and then this 3 is further connected with 4. Okay, now suppose if we want to find the parent of 4, then what we were doing, we are finding the parent of 4, that is 3, and then we will be finding the parent of 3, that is 2, and then we will be finding the parent of 2, that is 1. Okay, so this is how we are finding the parent of 4. But now what is happening here, in the worst case you can get a chain like this, and in that case if you want to find the parent of the last element, then you have to traverse each of the element and you have to move till the top. Okay, and this would be the worst case. In the worst case your time complexity would be, okay, in the worst case your time complexity would be order of n. Okay, and this is not something what you want to do. You want to make this operation efficient. So what you will be doing is you will be using the path compression method. So this is an optimization technique in find operation. Okay, so how we are going to do the path compression? So if you look at this particular path, so this particular path is a longer path. Okay, because this was the inefficient method of connecting the edges. But now suppose if we have connected the edges something like this, one is connected to 2, and again one is connected to 3, and again one is connected to 4. Suppose if we have, instead of connecting the graph like this, if we have connected it like that, then we can just find it in a single operation. Like what would be the parent of 4? So you will be finding the parent of 4, that is 1, and yes, 1 is the ultimate parent. So this would be a better approach. This would be a better approach. Okay, so here we are getting the longer path, and if you look at this path, so this is a shorter path. This is a shorter path. So that's why this is called as the path compression. Okay, so now how we are going to achieve this path compression? So like whenever I am finding, like suppose if I have find the parent of 3, so whenever I am calculating the parent of 3, I have to move to 2 and then I have to move to 1. Okay, so when I have calculated the parent of 3, I found that the parent of 3 is 1 itself. So when 1 is getting connected to 2 and then 3 is getting connected to 2, and now if I am finding the parent of 3, so if I am finding the parent of 3 at any point, I got to know that the ultimate parent of 3 is 1. So in that case what I will be doing is immediately I would be marking the parent of 3 as 1. Like we are just, if you look at our recursive function here in this line, we are just finding the parent, but as we are calculating this parent we can store it, and if we are storing it we don't have to find it again. Like suppose if we have already find the parent of 3, we can store it somewhere. Okay, so if we are storing the parent of 3 as 1, then now suppose if 4 is getting connected again, now suppose if 4 is getting connected again, and now suppose if I am asking the what is the parent of 4, so you will be saying the parent of 4 is 3, and you will be checking like the parent of 4 is 3, but the parent of 3 is 1, it is not 2, because you have stored it at this stage, you have stored it at this stage. Okay, so instead of moving this complete path, you have reduced your path. So this is path compression. So this is how we are going to achieve it. While calculating, we are going to store every value. Okay, so suppose if you are storing at this point, then at this point only your graph is going to look like this, 1 is 2 and 1 is 3. Now suppose if you are connecting again 3 with 4, so if you are connecting 3 with 4, you know that the parent of 4 is 3, and if you are again finding the parent of 4, so the parent of 4 would be, the parent of 4 would be 3 and the parent of 3 is 1. So now you know that the parent of 4 is 1, so at that time, at this time only you will be changing the parent of 4 to 1 only. So in that case it would be something like this, and you will change this thing. Okay, so yes, we can have an improvement here using the path compression. Okay, so we can implement that in our function while we are calculating the parent of x. We can store it also, like we can here only we can store it. So the parent of x would be find parent of x. So what this statement would be doing, it would be finding the parent of x, and it would be storing it in this particular thing. Okay, and after so first it would calculate the value of this, and then it would store it in the parent of x, and then it would return the parent and the value of the parent of x. So this will do my job. Okay, and now it is the efficient method using the path compression. Now can we do anything better in the union? Can we do anything better in union? Okay, so what we were doing in union, suppose we are having some graphs like this is connected and we are having only one node here, and now what we were doing, we were having, say this group is A group and this group is B group. Now what we were doing, at random we were choosing any point and we are making the other group as a parent of this group. Okay, now suppose if this was 1 and this was 3, now suppose if we are getting a query like 1 2 3, so what we are doing, this was the group 1 and this was the group 3, what we are doing is we are making the parent of 1 as equals to 3. Okay, randomly we are choosing any other person, like we are choosing the second person as a parent of first person. But now if you look here, you are making this person as a parent of this one. So if we are making this person as a parent of this one, we have to change like the parent of this to this, and the parent of this to this, the parent of this to this, the parent of this to this, like this. So it would be more like time taking, this would be more time taking. But instead of this, if you have like structure something like this, okay, if you have done something like this, if you have made this the representative of this thing as a parent of this particular node, then you, what you have to do is you only have to connect this particular node to that node and just this is done. Okay, so this is the less time taking. So this is the idea behind the optimization. So if you are talking about the optimization technique, so if you are doing the optimization in find, you can do it by two ways. One is the union by size and the another one is the union by rank. Okay, so this thing that we were doing, okay, so this thing that we were doing is the union by size. We were like checking the size, and what we are doing is we are making the parent of smaller size group to the larger size. Okay, this is what we were doing. So this was the smaller size and we were making this thing, this was the larger size, so we were making the representative of the larger size as a parent of the smaller size. Okay, so this is the thing we are always going to do. In that way we will be achieving the better time complexity. Okay, so this is the union by size. Okay, another thing was the union by rank, in which instead of the having size as the say parameter, so in the size what we are having the thing as a parameter, so we'll be counting the number of nodes, like the number of, if the number of nodes in a particular group is higher than the other, that means the size of this particular node is greater than the other. So this is what we are doing in the um, union by size. But if we are talking about the union by rank, what we are doing in the union by rank, we are taking depth into consideration. Okay, we are taking depth into consideration. Okay, and if the depth of the tree is higher, that means this thing is the, say the rank of this thing is greater than the rank of the other thing. So if you are taking depth into consideration, then in and then applying optimization, so that would be the union by rank. And if you are taking the number of nodes into consideration, so that would be union by size. Okay, but if you are using any of these two values, they are going to provide you the efficient approach for the union method. So they both behave in the similar manner, so you can use any one of them. So basically I prefer to use this thing union by size because it is more intuitive to me. So now we can apply the union by size method here in our approach. Okay, so what we have to do is, like, how we are going to get the size of anything. Okay, so what you can do is 1 2 3 4 5 6 7, like suppose if this was your initially the number of pupils, and first you are making a array, first you are making an array for the parent, like to store the parent of each person, and then you can again make the size like another array to store the size of the group. Okay, now suppose if one is getting connected to two, like initially the size for each of the size value of each of them, so this is the size. So initially the size value of each of them is 1 because they are independent single identity. Now suppose if one is getting connected to 2, so then one is going to behave as parent, like one is going to be the representative of this particular group. So what we are going to do is we are going to add the size value of 2 into the size value of 1. So the size value of 1 would be 2 now. Okay, so that means uh, the group which is represented by 1 is having size 2. Now suppose if 2 is getting connected to 3, so if 2 is getting connected to 3, what you will be checking is you will be making the parent of 3 as 2, as the ultimate parent of 2. Okay, so you will be finding, first you will be finding the parent of 2, so the parent of 2 is 1, and then what you will be doing, you will be making 1 as the parent of 3. Okay, so what you will be doing, you will be adding this size value to the size value of 1, so that would be 2 plus 1 is 3. So now the group that is represented by 1 is having a size 3. Okay, so this is what we are going to do. So we just need a size array to implement this. Anyone having any doubt till now, like what we have discussed till now? If you have any doubt, just drop a comment in the comment box. Okay, so with the parent I need one more thing, that is size. Okay, one more vector, that is size, and initially the size would be initialized by 1, like each value in the size would be initialized by 1, that we will be doing in our driver function. Okay, then what we have to look for, what we will be doing is we will be always making, if we are making say parent of px as py, then size of py is going to get increased. So the size of py is going to get increased by size of px, that we have already discussed. Okay, and then we have to always ensure that the px is a smaller size and py is a greater size, because we always make the group and the representative of the group of smaller size as the child, and the representative of the group of the larger size as the parent. Okay, so how we are going to ensure that? So by using a if condition. So if size of px, like if the size of this group is greater than size of, if size of this group is greater than size of that group, then what we are going to do is we are going to swap the groups. Okay, then we are going to swap the groups. Now if size of px is greater than size of py, what we are going to do is we are going to swap these two values. So in that case we are ensuring that the px is always going to be smaller. If it is going to be, if it is going to be the bigger one, then we are swapping it, and if we are swapping it, the smaller value is going to be present in the px. Okay, so now by this we are ensuring that thing. Okay, so I think now this is properly optimized. Okay, so we have already optimized our union and find structure. Okay, so we have already optimized. Let us discuss the time complexity. So if we are talking about the time complexity, so the time complexity would be say order of alpha n. Technically it is order of alpha n, because this is amortized time complexity. You cannot calculate the time complexity of this one directly, because it is very difficult to calculate the time complexity of DSU. It requires huge mathematics. So what is the alpha n? Alpha n is the inverse Ackermann function. Okay, and basically it is, this order of alpha n is almost order of 1. Why I am saying this order of alpha n is almost order of 1? Because it doesn't exceed, this alpha n doesn't exceed 4 uh, if say n is 10 to the power 600. So for this huge value of n, we are going to get alpha n as about 4. So that means this alpha, so order of alpha n is almost equals to order of 1. Okay, So this is nothing but the inverse Ackermann function. So it requires a huge mathematics. Okay, so yes, like someone is saying, so like I started studying data structure right now, and I'm not getting everything what you are teaching. So yes, definitely it happens if you have directly started with this lecture. So I'll prefer you to start with the first session and then um, watch the subsequent section, then you will be getting everything what I'm teaching. Okay, so yes, this would be the order of one time complexity. So the find operation would be again in order of 1, and the union operation is again the order of 1, almost order of 1. So this would be the time complexity for both the operations in the union and find structure. Okay, there are he's asking like where should we start to study the data structure. So like you can start from the GFG portal itself. We have a lot of blocks that is written for each data structure. Like you can search segment trees and you will be getting a lot of stuffs, lot of blocks that is written by say like experienced programmer as well as the college students also. So you can read those blocks, you can solve some problems related to that particular data structure, say solve 10 to 11 problems, and then you will be uh, you will get a good hold on the data structures. So just practice is the key. Okay, so yes, we have discussed the time complexity and we have implemented this. Now let us check this thing for our solution, like for our problem. So this is our union find structure or say disjoint set structure, and we are going to use it in our problem that we have discussed in the friends problem. Okay, so let me include the necessary header files. We need one main function. Let me put a gap here. We need a main function, that is our driver function. Okay, we need n, the number of friends. We will be taking its input and then we'll be assigning the values to them. So if n is the number of friends, what we can do is we can assign the parent, allocate the space for the parent as say n plus 5, just for getting rid of the um, segmentation fault, and then you can assign the size space for, you can allocate the space for this size vector, and that would be n plus 5, and we have to initialize it by 1. Okay, and then what we have to do, we have to make every node as a parent of its own, so that we can do. So yes, then we have to make it as parent of I is equals to I. Okay, so then we'll be taking a input, say we can define q m here and q 1m, and the another thing is q. Okay, so now we can take the input of m. M is the number of, like the number of inputs you are getting, like 1 is friend of 3, 3 is friend of 4, so that, so we have to take that also. So suppose if we are getting x and y, okay, now what we are going to do, we are going to connect them with each other using this union function, and then we'll be getting q queries, and each of the query would be asking for the two integers. Okay, now we have to check if these two x and y are friends of each other or not. So for that, what we can do, we can first find, we can just find the parent of x and the parent of y, and we can just compare it. So if the parent of x is equals to parent of y, not this, we can just check it by this, then what you can do, we can say that yes, these two values are friends of each other. Otherwise we can say that they are not friends. Okay, I think everything is fine, everything is looking good to me. Now let me check for some values. So suppose if we are having 6 people, if we are having 6 people, and suppose say 1 and 2 are friend with each other, say 3 and 4 are friend with each other, and say 1 and 4 are friend of each other. So like suppose if we are having 3 inputs, and then suppose if we are asking for 2 queries. Now if like 2 and 4 are friends of each other or not, or say if 4 or 6 are friends of each other or not. Okay, so now you can, from the input itself, you can see like 1 and 2 are connected, 3 and 4 are connected, and if you are connecting 1 and 4, then all of them are getting connected with each other. So 1 2 3 4 would be friend of each other. So if 2 and 4, if you are asking for 2 and 4, then 2 and 4 is going to be the friends of each other, and 4 and 6, so as 6 is only friend with itself only, and 4 is in this group, so 4 and 6 are not the friends of each other. Okay, so the first input should give friends as a result, and this other input should give not friends as a result. So let me check if we are getting the correct result or not. Okay, so we are getting some error. Let me check where we have made some mistake. Okay, size. So generally size is ambiguous because size is also a function name like vector dot size. So you cannot name it as size. So you can take some other name, say sz. Now let me check for this. Okay, so the first thing is giving me wrong output. So why? Okay. So here it should be parent of y. Okay, so now it is giving the correct result. So this is the implementation for this particular function. Okay, any doubt in the implementation, in the problem, in the solution, you can ask, or any doubt, just drop a comment, or we can just give you, I can give you the summary of the today's lecture. What we have discussed is disjoint set union. Okay, first we have discussed the basic approach. And then in the basic approach we have implemented two functions. One is the find, and the another one is the union. This find and uni function we have discussed. Then we have discussed the efficient approach. In the efficient approach, what we are doing, so in the efficient approach we are improving our find function by path compression. We have improved our find by path compression, and then we have discussed how we are going to say efficiently implement the union function. Okay, so that we have discussed by two methods. One was union by rank, and the another one was union by size. So basically they both behave in the similar manner, and you can pick any one of them. Both gives the same time complexity as a result. So I prefer to use union by size, and you can also go with this. So this is what we have implemented. So we have implemented union by using this strategy, union by size, and then we have implemented the find by a path compression. So this is what we have done in this lecture. Anyone having any doubt, just drop a comment. Okay, any doubts? or what we can say, we can discuss the application of this thing, as I am not getting any doubts. We can discuss the application. So we have talked like, yes, this disjoint sets are mostly used in say graph applications, so or say graph algorithms. So there are lots of graph algorithms which uses this disjoint sets. So the first thing is finding cycle in the graph. This particular the algorithm for this particular thing uses disjoint sets union. Okay, you can do it directly also by two-way coloring, but you can also use the disjoint set union also to find the cycle in the graph. Then second thing is it is used in finding connected components. Like you can do the find the connected components by using the simple DFS also, but the disjoint set can also be used in the connected components. Okay, so like we can quickly discuss these two applications, finding cycle in the graph and the connected components. So suppose if you are having some graph like this, and now suppose if you are getting a edge like this, so now this forms a cycle. So how you are going to check this? You can keep on adding the edge. So first you can add an edge, like if these are the number 1 2 3 4 and 5. So suppose first you have added an edge between 1 to 2, then you have added an edge between 1 to 3, and while adding edge you can check if the parent of suppose if you are adding edge between x and y, you can check if the parent of x, what is the parent of x and what is the parent of y. So suppose if px and py is the parent of x and parent of y, so if these two are not equal, you can say that yes, we can add edge. But if these two are equal, that means they already belongs to the same group and they are already connected by some means. And suppose if they are already connected by some means, and if you are again adding some edge, then this would form a cycle. So here you can see that uh, if you like leave this graph at this particular point, so you know that these are already connected. And now if you are going to find this 3, the parent of 3 and the parent of 4, you will find the same thing, that the parent of 3 is also going to be 1 and the parent of 4 is also going to be 1. And as these two are equal, and again if you are going to add an edge, so this would form a cycle. So this is how or where you can use the disjoint set union to find the cycles in the graph. Similar way you can find the connected components, like you can if you are given some graph like this. Okay, suppose if this is a graph. Okay, so this is a disconnected graph, but it is a graph. So now suppose if you are given a graph like this, so what you can do is you are getting these edges as your inputs. So you can keep on connecting this x edge with this x node with y by using this xy edge. Okay, and after connecting, you know that this thing would be represented by some particular parent. Okay, and this thing would be represented by some particular representative, and this particular group would be represented by some particular representative. So the number of unique representatives give you the result, give you the count of the number of connected components. Okay, so this is how you can use it to find the number of connected components. So this would be the application of the disjoint sets. There are many more applications and many more kind of problems where you can use or where you can apply this. So yes, I am done with this lecture or this disjoint set union. If you have any doubts, you can ask in the comment section, or we would be stopping our stream here. So as we are not getting any doubts, we are stopping our stream.